All right, so in this problem, we're dealing with two standpipes side by side with a narrow flow pipe connecting them. And let's say we call these two pipes just L and R for left pipe and right pipe. And we start off with some fluid, with lots of fluid in the left pipe and very little fluid in the right pipe. So let's label those heights as, let's say, height HL and height HR, height in the left pipe, height in the right pipe. And if we want to compare what's going on in these pipes, would you expect current to flow here?
The current would flow from the left to the right?
Yeah, we can expect current to flow from left to right. We get current flows from left to right. And why is that? What's causing the current to flow?
Difference in pressure?
Yeah, we've got a difference in pressure. If we compare the points, what would be some useful points to compare here? What are 2 points that have different pressures that causes the current to flow?
Surface?
If we take a look at the surface, what do we know about the pressure at this surface and the pressure on this surface?
1 atm?
Yeah, those are both 1 atmosphere of pressure. So these 2 points have the same pressure. So that's not, the pressure at the surfaces is not really what's driving current. But what points will have different pressures?
Sorry, is it the points like right under, like right before it hits like the bottom?
Yeah. If we go all the way down to the bottom, right at the beginning of the standpipe and right at the end of the standpipe, let's call those, let's say, 0.1 and 0.2. Why would we expect those 2 points to have different pressures?
Because of the different height in the water?
Yeah, this is under a lot of height of water. This is under only a little height of water. So we can expect high pressure at 0.1 because it's under so much depth of water. So 1 atmosphere plus rho g HL. And then 0.2 is going to be at low pressure because it's under only a little bit of water. So we'd have 1 atmosphere plus rho g HR from the Bernoulli equation. So we could even label those. We could say pressure 1 equals density times gravity times height left. And pressure 2 equals density times gravity times height of the right standpipe. And those also should both have a plus 1 atmosphere. But if we're talking about gauge pressure, we can ignore that. And we're going to be looking ultimately at a delta pressure anyway. So when we subtract, the plus 1 atmospheres will cancel out. If we write out a Bernoulli equation for just the flow pipe, Bernoulli equation from just 1 to 2. And we're assuming that fluid is going to flow from 1 to 2, so we may as well treat 1 as initial and 2 as final. What would be the Bernoulli equation for just those 2 points?
Delta P there's no height difference, so there's no rho g delta H.
Right, because points 1 and 2 are at the same height as each other. Even though they're under different depths of water, those 2 locations, 1 and 2, are at the same altitude as each other. So we've got no rho g delta H term. Should we expect any difference in speed between points 1 and 2? If we treat them as both part of the flow pipe?
No.
Because the speed only changes under what circumstances?
Area changes.
Right. And it looks like this flow pipe is consistent cross-sectional area. We can ignore the standpipes for now. If you just look at 0.1 as the beginning of the flow pipe and 0.2 as the end of the flow pipe is consistent cross-sectional area throughout. So we've got no kinetic energy density changes. We just got 1 and 2 being at different pressures. Do we have anything on the other side of the equation?
There's no pump, but maybe minus IR.
Yeah, no pump, but we should definitely expect a long, narrow pipe to have lots of resistance. And there's certainly current flowing through it. So we have a current times resistance dissipation term. And we want information about how fast is the current flowing. So if we solve for current here, just by dividing both sides by -r, we get an expression for how fast current is flowing. But ideally, it would be nice to fill in more detail for delta P. Resistance is just going to be some constant associated with the flow pipe, so we don't need to worry about that too much. But how can we write out our delta pressure here?
Oh, you can use the P from up there,
Yeah.
P1 and P2.
These pressure formulas, and these should be pretty consistent for any standpipe. Anytime you've got a standpipe, the pressure at the top is 1 atmosphere. The pressure at the bottom will be 1 atmosphere plus rho GH from the potential energy density term. You're losing rho GH worth of potential energy density and gaining rho GH worth of pressure. And if you're looking at gauge pressure, you can ignore the +1 atmosphere. And either way, even if you did have a +1 atmosphere, those would cancel out when we subtract. Delta pressure, and we're treating 1 as initial and 2 as final, even though everything is occurring at the same time. So P2 minus P1, the end minus the beginning. Subtract those. What can we factor out of those when we subtract?
Rho E and G.
Yeah, the density is the same because it's just one fluid throughout the whole system. The gravity is the same because everything's on the same planet. So factor out rho times G, and we're left with just height minus height. The difference between these two depths of water. So we get current equals negative rho times G times HR minus HL over the resistance. And of these, are any of these quantities not going to be changing as time passes? Are any of those constant?
Gravity and density.
Yeah, gravity and density should be constants. Also,
So should
resistance
resistance
depends on what resistance depends on what?
like how smooth or not smooth the surface of the area where it's flowing is.
Yeah, so that flow pipe itself. And also the geometry of it, the length and the cross-sectional area. But none of those are changing, so that means resistance is constant. So we can treat rho G over R as a constant. Also, I'm going to multiply this negative times both of these, so negative HR minus HL just becomes positive HL minus HR. That's also convenient because the higher height minus the lower height is going to turn into a positive number, which corresponds to a positive current, meaning the current really is flowing that direction. But we now have a formula for the current at any time based only on the difference in height. So when would you expect a very fast current? Or what would have to be true for the current to be very fast?
Would you expect the fast current? I said that it would be like in the very beginning.
Yeah, because at the very beginning, what do you notice about these heights?
That they're like very different from each other.
Right, and a large difference in height leads to a fast current. So at the beginning, there's a large difference, which leads to a very fast flow rate. But now there's less difference. Less difference. If HL minus HR is a smaller difference, what does that lead to?
Like a decrease in current, right?
But the current's not going to be as much. You're going to get a slower current. So if the heights are very different, they're going to be changing very rapidly. If they're less different, they're changing more slowly and more slowly and more slowly and more slowly. Is there any values you could plug in here that would make for no current at all?
When they're at the same height.
Right. If they're at exactly the same height, a height minus itself would be 0, so you get no current. Does that match with your expectations? If they're at the same height, should you expect no flow at all?
Yeah, because it's trying to even up the pressure.
Yeah, that seems to make sense. If they're at the same height, there's no difference in pressure at the bottom, so there's no reason for current to flow either direction. So that's the equilibrium situation. Static equilibrium would be if they reach the same height and then they would just stay there forever. Or alternatively, if they started at the same height, they would just stay that way forever. If they're not at the same height, they're going to approach the same height. But the thing is, the closer they get to the same height, the slower the current gets. So they're going to get closer and slower and closer and slower and closer and slower and closer and slower. Do they ever actually reach the same height?
No.
Mathematically, no, they don't. This would, if we graph this, this is going to be an asymptote. They're going to approach the same height, but never actually reach it. Physically, in terms of an actual example of this, they're going to get eventually close enough that it doesn't really matter. Also, for most fluids that we'd be dealing with on an everyday basis, like water, for instance, the fluid also has momentum. So as it travels, even though the pressures are balancing out, the fact that the fluid is in motion means it's going to try to stay in motion. So it's actually, physically, this might be expected to actually go past equilibrium and then oscillate back and forth, settling down on the actual equilibrium. But if we ignore momentum, then this is going to approach equilibrium but never reach it. Any questions on the math behind that so far?
I had a question for why is HR minus HL, why is it like that in the first equation, but then switched in the second one?
Because of the negative here. If we multiply this negative into both of these terms, because this negative can be treated as a times -1 multiplier. A negative distributes across addition and subtraction. So we get negative HR, that's this one here, and negative HL becomes positive HL.
Oh, I see. Thank you.
And generally for addition and even subtraction, order doesn't matter as long as you maintain what the negative sign is connected to. Like HR minus HL is the same as negative HL plus HR. Order doesn't matter as long as you keep the negative attached to the correct term. And then when we distribute this negative to both of these, negative HL becomes HL, positive HR becomes minus HR.
Got it. Thank you.
In the sense that, for instance, 8 minus 5 and 5 minus 8 are just opposites of each other. Any other questions on that so far? All right, then let's take a quick look at the graph of this. And it might be useful to make two graphs here because we're keeping track of both the height in each pipe and also the current flowing between them. So if we make a graph of height and current versus time, so time versus height and time versus current. And they start off at different heights. We've got two different heights involved here, HL and HR. So let's say HR starts off very small. We'll call that HR sub 0. Height, the left pipe starts off very high, H sub L 0. And at the beginning, there's a very large difference. What does that suggest about the current?
There's a bigger current.
Right, we start off with a very big current. So I'm going to put a mark high up on this axis and call it I sub 0. That represents our starting value of the current. So current starts off very fast. And these heights start off at these different values. Height of the left pipe and height of the right pipe. But current flowing very fast means what's happening to these heights as time passes?
It's getting smaller. The difference, I mean, between them.
Yeah, the difference is going to shrink because as current flows, that means the right pipe rises and the left pipe drops. We're causing the left pipe to gain water and the right pipe to lose water. And since it's a very fast current, these are going to be changing very rapidly. And on a graph of anything versus time, how would you see a rapid change? What would that look like on the graph?
It's like the asymptote is approaching 0. So it's going to be like almost a vertical line, but like kind of slanted. And then like it'll get very close, but approach 0 after some point. Like as the heights get closer and the rates are just like approaching 0, like the rate of flow rate.
Like exponential.
The steepness is really what matters here because and this will approach an asymptote eventually. But if we just look at it at this instant, large current means very fast rate of change, and rate of change is all about slope. So a very fast rate of change as time passes means we get a very steep slope. Right pipe increasing height very quickly, and left pipe decreasing height very quickly. But at this new instant in time, what do you notice about the difference in height?
It's smaller.
Yeah, smaller difference in height directly leads to smaller current. So the current decreases rapidly. There is still current flowing though, so the left pipe is still going to get smaller and the right pipe is still going to get bigger, but more slowly now. It's going to be a less steep slope due to the weaker current. And now there's even less difference in height, so we're going to get even weaker current. Weak current means they're going to be changing even more slowly, so we get an even slower increase in the right pipe and an even slower decrease in the left pipe. And once again, we've got an even smaller difference in height, so we get an even weaker current. And as this continues, the left and right pipe are going to get closer and closer to each other in height. But mathematically, they'll never quite reach each other. They're just approaching the same asymptote. And likewise, what's the current approaching?
0.
Yeah, the current is getting closer and closer to 0. Again, mathematically, we'll never reach 0. It's an asymptote. But physically, you'll eventually get to a point where the current is so slow it can't even be noticed. So we can round that off to 0. But mathematically, it's an asymptote. Any questions on those graphs so far? And what sort of function does this resemble?
Like exponential decay.
Yeah, this ends up being exponential decay. In fact, even the one that's increasing, even the right pipe, still technically counts as exponential decay. Even though it's an increasing function, it counts as exponential decay because it's approaching an asymptote. If we draw in this asymptote here, what's really shrinking here, what's decaying, is the difference between the value and the asymptote. Like if you look at this instant in time, the curve is this far away from the asymptote. If you look a little bit later, it's now this far away from the asymptote. A little bit later, it's this far away from the asymptote, and then closer and closer and closer. So really what's decaying here is the difference between value and asymptote. That's what's shrinking, the difference between the value of the function right now and the asymptote. And then a little later, it's closer to the asymptote, regardless of whether it's approaching from below or above. That still counts as exponential decay. Any questions on that so far? And one of the most important, I would say probably the most important property of any exponential function has to do with its derivative. If you just take some exponential function, let's say y equals e to the rt, where r is just some, actually I think they usually use lambda here, e to the lambda t. And in order to count as exponential decay, what has to be true about the exponent?
Lambda has to be negative.
Yeah, if the exponent is negative, it's going to be a function that approaches the asymptote. If it were e to a positive power times t, it would be growing away from the asymptote, either upwards or downwards, but either way, it would be going away from the asymptote. So let's assume that lambda is a positive number, but we put in a negative sign here. So e to the negative something t. And we could also have a constant multiplied outside the exponent as well. Let's say c times e to the negative lambda t. And the role of that has to do with the initial conditions. If you were to plug in 0 for t, what's e to the 0?
1.
So we just get at time 0, c times 1 is the y value. In other words, this constant multiplier is the y value at time 0. So we usually just write that as y sub 0. And the important result of this is what happens if we take the derivative. If you take the derivative of this function, y0 is just a constant, so we can just leave that in place, constant multiplier. What's the derivative of e to the something t?
Not the something, if it's a constant, can come in front, and it could be natural log of g.
Not a logarithm in this case. The
Oh.
exponential function, when you take the derivative, what happens to it? In general, the most important property of the exponential function is that when you take the derivative of it, you just get itself.
Oh, right.
The value of the function and the derivative of the function are the same, specifically if the base is e, 2.718, whatever. If you were to graph x versus e to the x, if at any location you compare the value, like how much of it there is, that's e to the x, and the slope, how steep it is at that instant. For y equals e to the x and e to the x only, the value and the slope are going to be the same. Like if this point has value y equals 3, then its slope will also be 3 at that point. That's what we mean when we say the exponential function is its own derivative. Take the derivative, you get the same thing as you would if you just get the value of the function. So the derivative of e to the negative lambda t is just e to the negative lambda t again. But because what's inside is not just t, we also need to multiply by the derivative of what's inside from the chain rule. And that's where the negative lambda comes from. In fact, in general, derivative of, let's say, e to the rx is going to be the same e to the rx, but also with a times r from the chain rule. So the e to the rx is describing how fast e to the rx changes, but also we get a times r representing how fast rx changes, how fast the part inside changes. So that's our derivative. Any questions on that so far? And the big important result of this is if you look at this portion of the function, ignoring the negative lambda, what is this part the same as?
The original function.
Yeah, that's the same as the original function with this extra times negative lambda. So the overall result of this is that anytime you got an exponential function, you get derivative of the function is this negative constant, or positive if it's exponential growth, times y, the function itself. This is the most important single characteristic of any exponential function. Its derivative is a constant multiplier times the original function. And this goes both ways because this is the only function that has this behavior. If you have an exponential function, then the derivative is a multiplier, constant multiplier times the function itself. And if the derivative equals a constant multiplier times the function itself, then you know it has to be an exponential function, with the exponent multiplier being this multiplier in the original differential equation. So in general, if derivative of y equals some constant times y, then y has to be an exponential function. So that's generally going to be true. Anytime you know that the rate of change of some value is proportional to the value itself, that's going to have to be an exponential function. And that's exactly what we have here. The variables don't quite match up in terms of units. We would have to do a few unit conversions first. But broadly, HL minus HR is some value. Specifically, it's the difference in height. The amount of difference in height And the rate of change of the heights are proportional because current tells you indirectly how fast the heights are changing. So this follows this same format. Rate of change equals a constant times the difference, or times the value right now. So that naturally leads to exponential decay. Any questions on that so far?
So what would lambda be in this case?
Sorry,
Would
what was
it
that?
be- what would lambda be like in the y equals y naught e to the negative lambda t?
Lambda is going to be partly the rho g over r, the constant we have here, but we're going to need to make one more change first. Because
Okay.
this setup assumes that y and y are the same function here. In this case, we've got heights here, but current isn't the derivative of height. Current is the derivative of what? What's flowing here? How do we measure how quickly it's flowing?
A times b.
That's one way we could do it. Yeah, current could be replaced as area times speed. And speed is the derivative of distance. In other words, speed is telling you how fast the height is changing. If the speed is like 3 centimeters per second, that means the water level is dropping by 3 centimeters every second. So we could replace V with, let's say, dH dt. And then A would be the cross-sectional area of these standpipes, which are both the same, so we can just use a single value for A. If we want this to look like this format, we would have to divide both sides by A. And now we have derivative of height equals a constant times the difference in height. So this would be our lambda here, rho g over Ra, the density times gravity over resistance of the flow pipe times cross-sectional area of the standpipe. So that would be lambda. And that influences how fast the decay is. Generally, a large value of lambda means decaying very quickly towards the asymptote. A value of lambda close to 0 means a much more gradual approach towards the asymptote. Any questions on that so far? And then interpreting that more physically, very high density fluid or very strong gravity would mean that it flows very quickly. I think that makes sense. If you're dealing with, like, let's say if you're dealing with mercury, which is much heavier than water, it's going to flow very quickly. Water is going to flow at more of a medium pace, and oil, which has low density, is going to flow much more slowly. So high density and strong gravity would lead to a very fast rate of decay. Whereas if you have a large area, like if the pipe is very wide, there's going to be more fluid to begin with, so it's going to take longer for it to flow. So large area means slower rate of change in height and lots of resistance. If the flow pipe is very narrow, if it has lots of resistance, you're going to have a much slower change in height as well because it's more difficult to flow.
Oh, so I just wanted to check why and why not here would be I and I not, right?
For
Or is
this,
that like
one,
different?
for this one, we could just say I of t equals the starting value times e to the negative lambda t.
Okay, got it.
This one is made, or these two are made a little more complicated by the fact that they're not approaching 0. They're approaching this height instead, equilibrium height. Let's say HEQ. So what you need to do there, if you wanted to take an exponential decay graph that approaches 0, but shift it so it's approaching some other equilibrium value instead, what do you do to an equation to shift the graph up or down? Like if I've got this graph,
y-intercept?
yeah, we can just add a constant, right? If you want to shift the exponential decay graph up so it has a non-zero asymptote, you would just have plus some constant outside the function. So for these ones, we would write it as something like h equals h naught times e to the negative lambda t, using the same lambda because it's the same situation, plus h equilibrium. that shifts it up so it has a non-zero asymptote. One thing we need to change though is H naught, because we don't want to use the H naught that we had for these values. If we do, when we plug in 0 for t, we get H naught times 1 plus this other value, which we don't want. So instead what we should have here is a modified value. Specifically, if we have H naught, that multiplies by 1 at times 0, because e to the 0 is 1. But we don't want to have an extra plus H equilibrium. So we can have a, to cancel that out, minus H equilibrium here. So our multiplier, in this case, if we have a non-zero asymptote, we're going to have starting value minus equilibrium value times the exponential function plus equilibrium value. That sorts out to a function that starts at the correct equilibrium value and approaches, or starts at the correct starting value and approaches the equilibrium value you want. Any questions on that? Or exponential decay in general? All right, then let's try out a electrical circuit problem. Get some more practice with that as well. All right, so let's say we have this electrical circuit. We've got a 96-volt battery, 4 resistors with values 1 ohm, 6 ohms, 9 ohms, and 3 ohms. So we know the voltage, we know all the resistances. What's unknown here, though? What important quantity is not labeled on this diagram?
Current?
Yeah, the current's not labeled. So in a situation like this, let's say our goal is to find the current. And how many different currents would you expect to see in this circuit?
Would they be different for each of the resistors?
Almost, but not every resistor is going to have the same, not every resistor is going to have different currents. For instance, let's say you've got current flowing through R4. Where does that current go next?
To the battery,
To the battery and then,
to resistor 1.
right. So since those are all in the same path, those will all have the same current. Let's just call that I1. But then when that current hits this junction, what's going to happen?
Would all the current or half of it would flow there?
What do you mean half?
Half of it would flow to each of the different parts of the junctions?
So half of it this way.
Or maybe the
this
same.
way.
I'm not sure.
Would we expect those to get the same amount of current when it splits? Should we expect it to split evenly?
I think no, because it has 2 different resistances.
Right, these resistances are different values. The only time, anytime current hits a junction and there's multiple paths, it's going to split amongst those multiple paths, like the amount of current splits up. The only time you should expect it to split up evenly is if the paths have equivalent amounts of resistance. The paths don't have to look identical, they just have to have the same total resistance. Like if this was 9 ohms and this path had a 6 ohm resistor and a 3 ohm resistor in series, the total would still be 9 ohms, so those would be equivalent. In this case, though, one path has 9 ohms, the other path has 6 ohms. So it's not going to split up evenly. Which path would you expect to get more resistance? Or sorry, more current?
The one with less resistance.
Yeah, the one with less resistance gets more of the current because it's easier to flow that way. The one with more resistance does still get some current. It just doesn't get as much current. So let's call those I2 and I3. We don't know their values yet, though we do know I2 is going to be greater than I3. Also, how should we expect, excuse me, how should we expect all three of these currents to relate to each other?
I2 plus I3 would equal I1.
Yeah, I2 plus I3, the total current flowing out of this junction, has to match I1, the total current flowing into this junction. You can do the same thing with this junction as well. Total current in would be I2 plus I3, total current out would be I1. So either way, you get this equation from the junction rule, which is basically just the electrical version of the continuity principle from fluid flow. Total current in has to equal total current out. It's not like we're getting charge just vanishing or appearing out of nowhere. So that's a useful equation linking those three together. But we're going to need more information because we currently don't know any of those three values. So let's apply. We could use a system of equations approach, but that tends to be really tedious. Often a much easier way to do this is to simplify the circuit first. Are there any pairs or trios or whatever of resistors that you could combine together and say these act like just one big resistor?
Resistor 4 and 1.
Yeah, if you take a look at resistors 4 and 1, these two resistors together are connected in what sort of way?
Would it be parallel?
And why would they be parallel? How can we tell?
I wasn't actually sure, but I was thinking since they're like right on top of each other, it could be that.
Kind of look right on top of each other, but keep in mind you can't necessarily trust just where they appear in the circuit in terms of physical location. For example, if you've got, let's say, these two resistors, just based on their placement, you can't really tell. What's important is how they're connected. If you connect them like this, how would you say that connection is?
In series.
Series.
This would definitely be in series. But if we instead keep them in the same place but change the wiring, if we have the wires look like this, these would now be in parallel. We haven't moved the resistors at all. We've just changed how they're wired. And if you take a look at the path, we've got one path that splits, and each resistor is on a separate branch in those two paths. So these would be in parallel. So the important thing to ask is, are these resistors on the same path, or are they on separate paths of some split? What is a better description of R1 and R4 here? Are they on one single path, or are they on two separate paths?
Like on one path?
Yeah, this is just one path. It's a curved path, but it is still one single path. So we would say R1 and R4 are in series with each other. The fact that there's a battery in between doesn't really matter here. The important thing is that R1 and R4 have to have the same current. That's one of the most important properties of series. Series means has to have the same current. And if they're in series, how can we combine their resistances?
You can add them up.
Yeah. If they're in series, we can just add the resistances. So let's say R14 equals R1 plus R4. So that'll be 4 ohms. So these two resistors together act like just a single 4 ohm resistor. So we can simplify this and say we've got a 96 volt battery, and then we can combine those on either side. Doesn't really matter where we put it, as long as it's on that path. And say these two together act like a 4 ohm resistor. Meanwhile, what about these two resistors? Are they on the same path or are they on parallel paths?
They're in parallel.
Yeah, we've got this split in the path here. These are on two different bridges, starting at the same point, but going in two different ways to end at the same point. So we would say those are in parallel. And how do we combine resistors in parallel?
1 over R3 plus 1 over R2 is equal to 1 over like the equivalent resistance.
Yeah. So 1 over R total, which I'm going to call R23, equals 1 over R2 plus 1 over R3. So 1 over the total, R23 equals, and how can we add these together?
You find a common denominator, so I think it's 36.
Well, the 3 is a common factor, but what's a common multiple? What's the smallest number that's a multiple of 6 and a multiple of 9?
18.
Yeah, 18 should work. And by the way, it doesn't have to be the smallest. We could just use any number that's a multiple of 6 and a multiple of 9, but the smallest one is going to be the easiest to work with. So to change 6 to 18, I'm going to multiply by 3, both in the numerator and denominator. To change 9 to 18, I'm going to multiply by 2 in both the numerator and denominator. So we end up with 3 plus 2 over 6 times 3 or 9 times 2. In both cases, that's 18. And then to actually find R23, we just need to invert both sides. And we get R23 equals 18/5 ohms. Or as a mixed number, that would be 3 and 3/5, or 3.6 ohms. So that's the value of R23. R2 and R3 together act like a single resistor whose resistance is 3.6 ohms. And at that point, how would you say R14 and R23 are connected?
Would they
In
be both in
series.
series?
Yeah, these are definitely in series, so we can just add those together. 4 plus 3.6 would be 7.6. So our total is 7.6 ohms. And now we have a simplified circuit. We're essentially saying this whole complicated mess acts like just this one simple loop. And in that simple loop, how can we figure out the current? Can we set up a loop rule for that? Yeah, use the voltage of the loop. In any single complete loop, the sum of all the delta voltages has to add up to 0. In the simplified version, we have just a single battery and a single resistor. So that's delta V of the battery plus delta V of the resistor. Battery is just going to be our plus epsilon, our 96 volts. Resistor is going to be minus IR. How would we isolate I there?
You can move IR to the other side and then divide E by R.
Yeah. So I is just going to be epsilon over R. And you can generally use that anytime you've just got a single loop with one battery and one resistor. The current is just going to be epsilon over R. We can then plug in those numbers, 96 divided by 7.6, and we would get about 12.63. And that's specifically the current going through the battery. So we now know the current going through the battery. And that's going to be the current through R4, the battery, and R1. As soon as it hits the junction, it's going to split up into I2 and I3. So we would still need to figure out how it splits up. But we can actually do that pretty quickly just by starting to label voltages. What I usually do is label the point right before the battery as 0 volts. We go through the battery. What does the battery do to voltage?
Increases?
Yeah, it's just going to cause an increase. The negative terminal, the short bar, is going to be the low voltage side. The positive terminal, the long bar, is going to be the high voltage side. So this just creates a difference between low voltage, which we're calling 0 volts just as a reference point, and high voltage, which is going to be 96 volts higher. And these don't have to be labeled 0 and 96. You could call these like 1000 and 1096 or whatever values you want. The important thing is that they're different by 96 volts. Then we go through a resistor, and what happens to the voltage?
A drop.
It drops, and it specifically drops by I times R. We know the current, we know the resistance, so we can multiply current times resistance to figure out how much the voltage drops. So just multiply 1 times 12.63, and we get 12.63 volts. So from here to here, we're losing 12.63 volts. So if we just subtract 96 minus 12.63, we get 83.37. So this point would be 83.37 volts. Because we know how much we started with right before the resistor, we can multiply I times R to figure out how much we're losing, subtract to figure out how much is left. So that's the voltage here. And in fact, that's the voltage in this entire region. If you go from a point to a point just going through wire, those points connected by wire have to have the same voltage. Because wire does not, like just wire doesn't cause a voltage drop. It has effectively 0 resistance. So we now know the starting voltage for both of these resistors, but we don't know the ending voltage yet. So we're going to have to backtrack from 0 volts. If you go backwards through this resistor, can you figure out the voltage drop for this resistor, the 3 ohm resistor? Do we know the current there?
Yeah, it's 12 point.
Yeah, 12.63 amps. So we can multiply current times resistance, 12.63 times 3, and get 37.9. So that's the voltage drop across this resistor. From here to here, from start to finish, we're losing 37.9 volts. So if you start somewhere and lose 37.9 volts and end at 0, that means you had to have started at 37.9 volts. So that you can lose 37.9 and end at 0. So by backtracking, you can think of this as the high voltage side and low voltage side, since current flows from high voltage to low voltage across a resistor. And now we know the starting and ending voltage across R2. Subtract those, 37.9 minus 83.37, and that tells you the delta voltage. And then you can use delta V equals negative IR.
Wait, sorry, how did you find the 37.9 volts again?
That was from multiplying current times resistance for just resistor 4.
So you do 12.63 times 3?
Yeah, delta V is going to be 12.63 amps times 3 ohms, which is 37.9 volts. And we should treat that as negative because it's a voltage drop. But that means in the direction current is flowing, we're losing 37.9 volts. If you lose 37.9 volts and end at 0, that means you must have started at 37.9 volts. You can think of this as going in reverse. If you go backwards through a resistor, you're gaining voltage.
How did you know that it would be right after I2 and say like not after I3? Like how did you know it would be that point right there and not the one?
It's
to the
actually
right?
this entire region. This entire region, all this stuff that's connected by just wire is all at the same voltage. So this point is also 37.9. Every point along these wires, up until we actually get to the resistor itself, is all at the same voltage. As soon as you cross the resistor, you're changing the voltage. But if you just go through wire, all those points connected by just wire are the same voltage as each other.
Got it. Thank
So
you.
this entire region is 37.9 volts. This entire region is 83.7 volts. Each one of these resistors, R2 and R3, acts as a bridge from a high voltage region to a low voltage region. You can subtract those voltages, 37.9 minus 83.37, to get the delta voltage. And then you know the resistance, so you can solve for the current in each one of those branches. So that difference in voltage divided by 6 ohms tells you current 2. The same difference in voltage, because they're in parallel, divided by 9 ohms tells you current 3. And then as one final check, you can add current 2 and current 3 and make sure they add up to 12.63, or close enough to be a rounding error. And at that point, you have all the currents in the entire circuit, and you know all the voltages of all the important regions as well. And that's pretty much everything that can be known about the circuit, or everything that needs to be known anyway. Any questions on that?
Yeah, I have a question about the difference between just voltage and the voltage drop. So like at resistor 1, which is 1 ohm, is 12 point something the voltage or the voltage drop?
That would be the voltage drop, because the voltage right before is 96 volts. The voltage right after is 83.37 volts. The difference in voltage is the voltage drop that we're talking about.
Okay, so then for resistor 4, the voltage drop is 37.9.
Yeah.
Okay, thank you.
Because that's the difference between the value on one side and the value on the other side. And then same thing for instance, R2. The voltage drop would be the difference between these values, 83.37 minus 37.9. And since R2 and R3 are in parallel, they have the same voltage drop because there's just two different paths that start at the same starting point and end at the same ending point. They start at the same high voltage, they end at the same low voltage. Any other questions on that? All right, and if you want to get some more practice with circuits, I've got a worksheet of just a bunch of circuits where the voltages and resistors are labeled, and your task is to find all the currents on mathandcheese.org. So math.andcheese.org/P7B, and look for the link to the circuits practice worksheet.
Thank you.
So give that a try to get some more practice, and I will see you next time.
Thank you so much.
You're welcome.